me just meet everyone and then make a couple of you co-hosts. Good morning, everyone.
Good morning.
Nice to see you with video. Barely remember what you looked like, Chris.
Usually I'm having breakfast, so I don't put the video on.
That's fine, no need to justify yourself. It's just lovely to see you again. Right, let me just share the paper over on YouTube as well. Hang on. Oh, God. Can one of you just check that we're streaming to the right channel?
Okay, we look.
Hi, Victor.
Good morning.
Just realized I'm still logged in as OHBM, but it seems to be working. So before I change it.
No, it's okay. It's in Neuroccino live.
Okay. Well, let's see if this works then. No need to fuff around. Okay. So just for everyone over on YouTube, don't be irritated. I'm the Organization of Human Brain Mapping today. On the wrong account, but it's working. So we leave it as it is for now. And I'll try to fix that later. Great. Well, welcome everyone to Neuroccino, our Monday morning journal club, where everyone is welcome to present a paper. Today is going to be me. I know, trying to multitask. So if anything doesn't go well, like being logged into the wrong account, I do apologize. But the way it works is everyone is welcome to come and present a paper, a book chapter, anything exciting they read and want to share. The only thing we ask is that you don't present your own work, so no self-promotion. And that's basically it. Now, today's paper, I already shared it with you in the chat here and over on YouTube, but let me share my screen so we can all see it. There we go, that works. Lovely. Okay, so this is a paper from Nature Communication entitled A Low Cost and Shielding-Free Ultra-Low Field Brain MRI Scanner. I have to say they just started works outside. Hope it's okay. There were so many papers this week to choose from, so I went with the one that is open access because the other ones were hard to get access to. This is an exciting paper because they basically talk about MRI being a key tool in healthcare, that every year over 150 million assessments with MRI are conducted, that it has the great advantage of being non-invasive, non-ionizing, quantitative, and has a multi-parametric setting, i.e. you can acquire many different types of scans that are sensitive to different parameters. And they say that the success story of MRI comes down to the collaboration between scientists, clinicians, and engineers. So all is well and good, but there's a big but. And the big but in this paper is that about 70% of the population have no or limited access to MRI scans because they are very expensive to acquire. They are very expensive to run in terms of the actual running costs, but also the expertise that is required for it. And that altogether makes it a high-tech tool that is only available or mainly available in the to like 30% of the world's population, and usually is hosted in shielded complex rooms, MRI suites. I'm sure most of you here have seen it in real life already. Somewhere hidden in the basement of a hospital usually, or some kind of assessment clinic. So obviously, MRI is an essential tool both for research and for clinical research, diagnosis. But because it's not really widely available still at this point, they came up with a new way of building a MRI scanner that you can literally just plug into any socket. That is low cost to build. If I'm not mistaken, it was less than $20,000 US. It's compact, mobile, and acoustically quiet during scanning. Though I have to admit, I haven't checked yet against silent MRI if that's about the same. And they can actually acquire T1, T2, FLAIR, and DWI sequences, which are the most common sequences run in a clinical setting. Sorry, I hope you can't hear this, but this is really doing my head in right now. In the paper, they then went on to not only say, look, we built this super machine, but we can even use it to diagnose the most common neurological brain disorders, like tumors and strokes, for example. And then they took it one step further, which I thought was fantastic, to also look at artifacts due to electromagnetic or ferromagnetic implants in the body. So why did I think this was an exciting paper? Well, many reasons. First one is that the majority doesn't have access to this technology. So by having methods or techniques that are more compact, mobile, and affordable, we can actually ensure that everyone has access to this fantastic tool for healthcare. But also, coming from a stroke background, time is brain. So the first scan is important in deciding the treatment pathway for stroke patients. In the beginning, you want to see if it is a bleed or an occlusion, because those are two very different treatment plans. And for that, you don't need the fanciest 3T, 70, 90, however many Ts you want scans. You literally just need a quick picture of the brain to see how you can help the person. And the sooner you can get that picture, the better it will be. And ideally, one day we can actually just, at least in our parts of the world, I guess, have a portable, maybe just an MRI hat in an ambulance. So you can scan people on the way to the hospital. So by the time they come into the clinic, they already are set for their treatment, and we can save more brain tissues, and by that, more quality of life and patients overall. Now, our regular listeners will know that I'm no physicist, I'm a psychologist by training, so I'm not even going to try and explain the physics of this scanner, but we have very capable physicists in the room. So this is the setup that I quickly wanted to show you. Yes, I was right. It was less than $20,000 US to build this machine. And you can see that it's not a full body scan at the moment. It's head, shoulders, chest, a little bit. So it's a lot less claustrophobic, you could argue, than the normal bore of the scanner. As you can see from my notes, I was wondering if this is movable. This looks very rigid to me. And because I was scanning a lot of stroke patients, a lot of them do come to the scanner in a wheelchair. So I was wondering how you get people up there, because it looks quite high to me, but that's just, I guess, a minor detail once this is sorted. And then you probably wonder, well, how good can it be if we're scanning at, you can see here, 0.055 T. So I want to quickly show you the brain images. So this is, sorry, just before I show you the pictures, this is an important thing. So why is this revolutionary and made it into a Nature journal? It's because they developed a deep learning algorithm that can detect and cancel out electromagnetic interferences from outside and inside the scanner, which is the new thing. Again, I'm not going to go into the details of this, but you're welcome to read it. So let's look at the pictures, which is the exciting bit. So these are pictures acquired in healthy adults, and they say that for all three sequences, so T1, T2, FLAIR, and DWI, it takes about 30 minutes. Now, let me see if I can zoom in a bit. So obviously, if you're used to super high resolution, this is not a great resolution to look at in terms of knowing your way around, knowing your anatomy. But the cool thing is when we skip to, this is the diffusion, which has a p-value of 500, just for those in the know. When we skip to the patient, it gets really interesting because you can clearly see the lesion here on the T1, the T2, not as clearly on the flare, but definitely clearly on the DWI. And this is comparing the 0.055T to a standard 3 Tesla scan. Obviously, this is a brain tumor, and it shows up nicely on all the different scans. Then here we have trauma, which I guess is a little bit harder for the untrained eye to appreciate because it doesn't stand out as clearly. And then sounds horrible, but my personal favorite is the stroke patient. So this is acquired 3 weeks after the 3T scan. And they even managed to capture what is known as pseudonormalization. That is that over time, the signal in the images changes. And if you acquire the image at a sweet spot, the picture looks like there is no lesion. But that depends on the picture that you acquire. So you may not see it in the ADC, but you could see it in T1 and vice versa. So it changes. It's a dynamic evolution over time. But you can clearly see, even some might argue better on the low-cost MRI here, the lesion compared to the 3T. You can see it on the flare. You can definitely see it on the DWI and the ADC as well. And this is the ischemic stroke, which means it's a vessel occlusion. And then we also have the hemorrhagic stroke, which is a lot less common. But you can see the lesion very nicely highlighted on the low-cost MRI. So this is super, super exciting. And here they scanned the stents and clips to show the artifacts and actually showed that there's very little artifacts due to implants. That is basically the paper, or the parts that we just check. Yeah, why I'm super excited about this, and I happily try and take your questions. No questions? There we go, Michelle.
It's so cool. When are we building one?
Do you know, we always have a summer project. We're quite busy this summer, but next summer there's an opening for a new project.
We got a lot of project going on, but this would be good to go for the Neuroscience Alliance.
Oh yeah, absolutely, absolutely.
Thank you. It's great.
Well, I just presented it. Had nothing to do with it. Leah, you have a question.
Yes, I was just thinking about the pros and cons of this med. I was thinking that, yeah, as you said, it's great because it's low cost. Maybe a lot of people can assess to that. But then I was thinking now where it's going the direction of MRI, that you want the fanciest image ever. So I was thinking, do radiologists will accept these kind of blur images, or well, I was wondering, how these can fit in the current reality.
Well, it's kind of this or nothing, no? That's the point.
Well, it kind of depends on what the purpose of you scanning is and where in the world you are. So if you want to go for super duper pushing the frontier neuroimaging, this is probably not the right tool for you. If all you're interested in is a quick assessment of what does the patient need, especially in conditions where time is brain, then this is a lot more accessible than our fancy MRI scans. I'm assuming. I haven't looked at how to build it, so maybe it's actually
No, because like when I was working in the hospital like this, usually when an hospital gets like the new MRI, so for example, passing from 1.5 Tesla to 3 Tesla, there is all this market of the second-hand MRIs. So that maybe can be better than this, but maybe achievable also from other hospitals. But I was thinking that this technique is great if some people have some contraindications for going in high field. So in this case, this can be an option because everyone, like, there are no contraindications for this one since it's so low field.
Yeah, I mean, it will be a game changer for clinical diagnosis, not necessarily even research, but for clinical diagnosis, this will be a game changer, especially to the 70% of the world that currently have no or very limited access to scanners. I just skipped to the part in the paper that I wanted to show you. There is already a low field MRI scanner that is also operating in unshielded environments that is FDA approved already. So this is definitely something where the field is going, but I think there's a divide between, as often, between the research world that is pushing the gradients and the Tesla strength and everything to be better and better and better, and the clinical world that oftentimes still doesn't even have a 3T scan. And as they argue in the paper, we acquire all these fancy methods to do tractography, to do functional imaging, but like coming back to the example of stroke, you don't need that. The first thing you need to know is an occlusion or a bleed, and that will dramatically change your care pathway. And for that, this is a great tool. And as I said, if I know there's a lot of companies working on it as well to do like a head-only scanner, and I've been hearing about this for many years. I haven't actually seen it yet myself, but if that is something that will be feasible in the future, and you could actually scan patients in the ambulance on the way to the hospital, no idea how you deal with the motion artifacts in that case, but talking ideal world here, then this will be such a game changer that will save lives.
Yeah, for sure, really easier to build than the actual MRIs for the shielding. Yeah, that for sure, it's really more practical. I agree, totally.
Victor.
A really good paper. I'm really excited about this kind of technology, and especially about the possibility to sell them to low-income countries. I think these are the places where it might make the most difference, at least today, because you mentioned the potential use for quick fMRI in the ambulance, or maybe in the hospital, but very fast and stuff like that. And I'm not sure this is the tool, because this kind of thing, this kind of machine, I expect them to take quite longer to get a quality image compared to a classical 3T scanner, I guess, because you've got to do many more passes on the same voxels to get as much signal as you can to have actually proper data, I assume. I don't know. It's just
it was 30 minutes in total for all 4 acquisitions.
It's all 4 acquisitions, not just one acquisition. Okay.
No, it's all 4.
That's not bad. That's not bad.
It's not bad at all.
Yeah. I mean,
especially that because you don't always need all of them. Like for stroke, for example, if you want to see occlusion or bleed, you can just run one of the sequences and you have your answer.
Yeah, and then there is always the problem is in the ambulance, all the motion, but you talked about it like briefly. So I'm probably not quite there yet, but that gives it hope. That's right. But
also, in terms of the resolution, they acquired 2x2x10 for the structural images and 4x4x10 for the DWI, and then reconstruct the resolution to 115.
Okay, that's good to know too. Yeah.
But yeah, so just to coming back to the first thing that you mentioned, that this will be a great technology to sell to other countries that may not have access to the 3T. I think just selling it may not do the trick. I think we should, as Michelle said, build it, but also teach other countries how to build it so they can then self-maintain it, run it themselves, teach the next one. So each one teach one, basically.
Sure.
And that this way you pass it on rather than going with the old school model of, hey, we built it, we sell it for a lot of money to you. I think this will be a much better snowball way of rolling out those machines to the 70% who currently doesn't have access to it. Wow. Okay. I think Valentina was first.
Just a brief comments. I still think that other country who doesn't have access to high quality level MRI scans should have access to high quality level MRI scans, not the portable, friendly user, a low resolution MRI scans. That's it.
Absolutely. And I didn't mean to say they shouldn't have access. I'm just, for the time being,
no,
this is
we're not saying that. We're not saying that, but just
put it on record.
they should know. They should not be happy with it, and that's it.
I don't know who was first. Chris is first on my screen, so there you go.
All right. So is it open source, the how to build the machine? Do you know if it's open source or not?
Good question. I have not.
Can I print it with my 3D scanner, my 3D
Yes.
printer?
I was not trying to say that earlier, but yes. I haven't come across it in the paper, but maybe in the supplementary.
Because that would be awesome especially for low-income countries. And also I have another question. Do you think, or comment, do you think there will be some methods maybe using high resolution MRI to improve the low resolution of these machines? So there are some algorithms, like some, I think it's called super resolution, that can fill up the slices if you have a very low resolution in one dimension of your MRI. And there are also other kinds of algorithms that can improve lower resolution MRI. So do you think it could help having a better resolution for these ones as well?
I guess potentially, yes, but bear in mind that the resolution of this one isn't actually that bad. Like, I was quite surprised by 115 or 2210. I would have expected the resolution to be even lower, to be honest. But I saw the physicist in this chat, not when you asked the question. So I'm going to pass it over to.
No. Like when you talk about super resolution, maybe they already applied when they passed from 2 millimeters to 1, I guess, yeah. Because they did the deep learning for the noise subtraction, and probably usually when I see an experiment of hyper resolution, that they pass from 2 millimeters to 1, so maybe it's kind of the same, but I have to check.
Happy with that? Cool. I mean,
yeah, it's very exciting, and I think the implication for clinical use is very obvious. But I also think it could be potentially very useful for research as well. If you want to acquire multiple, like, longitudinal scans, often we're limited by. I don't know how much the cost is usual limitation, but I mean, obviously, if it costs much less, you could be scanning more people and more time, with more time points, which
yeah,
could be
absolutely
important
right.
for different field of research, how longitudinally brain changes in different clinical conditions or even in normal development. So, I mean, as you already mentioned, there's already been like deep learning algorithms to be able to, let's say, segment brain tissues from lower quality images. Like in FreeSurfer, there's like SynthSeg that use deep learning to be able to use very poor quality images to get the very robust tissue segmentation. So I guess if people start using this more widely, I think there's different possibilities for the research as well.
I mean,
yeah.
It could also be like a nice tool for students or like other side projects. So you're not clogging up the time on the big clinical machine that is actually needed in a clinical routine, but you can, for just proof of principle and simple, and by simple, I mean not fancy sequences, you could definitely have that scanner in like a cupboard and plug it into a normal socket and run an experiment in your spare room. In theory, it's like insane, the possibility that opens up. So yeah, very exciting. And you're right, it can, for some questions, it can also make it into research. Michelle had another question.
Yeah, I've seen like some clinical scans that are actually very comparable to the quality of, well, images coming from 1.5 or 3 Tesla from the clinics that are very comparable to the quality of the images that we see here with this relative $20,000 MRI scan. So in a sense that, yeah, I'll agree with Valentina, and it's true that everybody should have access to top-notch technology, but we cannot, well, we don't have the money to pay. Like personally, I don't have the money to pay an MRI scan to the country I'm going to, but this is an opportunity for us maybe to do something, you know, something better for, that is like, you know, affordable and feasible at our level if we travel and we collaborate. So just see it as like great value.
I don't want to burst your bubble here, but it's still not quite as portable as you putting it in your luggage.
No, yeah. Well, you know, you get what I mean.
Depends on how you travel, but it's still a big machine at the moment. I'm sure you'll find a way. Yes. Are there any other questions? None I can see here, none over on YouTube. Well, in that case, we're actually perfectly on time. Thanks for joining us this week. There is another Neuroccino next Monday morning, 9:30 Paris time. Everyone is welcome to present a paper, a book chapter, as I said, anything that gets you excited, and just tell us why got you excited. Volunteers are welcome. And apart from that, have an exciting week in science, and we shall see you next Monday. Bye.